let's now look at an implementation of PCA and, most importantly, how we actually do the dimensionality reduction. All right, so we're gonna stay in R2. We'll go into higher dimensions in a little bit, but let's stay in R2. So let me generate 1,000 data points. I'm gonna generate a bunch of X coordinates, and I'm going to, so that's the X coordinate in this two-dimensional space. Let me let the Y coordinate be some scaled version of X plus a little bit of noise. That's the purple data points here. You can ignore the cyan line right here. We'll come back to that in a little bit. So my data don't line a line. I think we can agree on that. But it's clearly has more variation along this dimension than it does along this dimension. Okay, so we'll come back to that in a little bit. All right, so I've got a bunch of data. It's in a two-dimensional space, and now I'm looking for a new basis representation that will diagonalize the covariance matrix and eventually reduce dimensionality. So let's run through PCA. First things first, let's zero mean the data. The X component gets X minus the mean. The Y gets Y minus the mean. Again, we're zero meaning because we're going to compute variances and covariances, and we need to have the data zero mean. Let me create my data matrix. I'm going to pack into the row X and then row Y, and then I'm going to compute the covariance matrix. So this is a 2 by n matrix. This is going to be a 2 by 2 matrix, the covariance, D times D transpose. All right, I've got my covariance matrix of my zero mean data. And now what do I want to do? We said that if we create a new matrix B that has the rows in it are the eigenvectors of this covariance matrix, well then that will diagonalize the covariance matrix of the new data with respect to that basis representation. Okay, let's go ahead and compute the eigenvectors of the covariance matrix. So I'll grab the eigenvalues and the eigenvectors right there. And what do I now want to do? I want to project the data onto those vectors. So let me just grab P1 and P2 as the two eigenvectors. That's my new basis representation. And let me now just go ahead and visualize everything before I do the dimensionality reduction. All right, the blue or cyan lines that you see here are P1 and P2. And in particular, P1 is this one right here, which is the larger of the eigenvalue of the eigenvectors. I returns things in sorted order, and this is the smaller. So a couple of things to notice. First of all, it's perpendicular to each other, the basis. By the way, that's guaranteed because all eigenvectors of any square matrix are perpendicular to each other. It has to come out this way, and they're also unit length as well. And so notice that this vector, the new basis, and this are perpendicular to each other. Notice also that one of the eigenvectors is along the axis of which the data is maximally covarying, and the other is where it's covarying a lot less, or varying a lot less. And so I haven't reduced dimensionality yet. Why? Because I still have two bases onto which I want to project my data. This one and this one, as opposed to the canonical this one and the canonical this one. But can we agree that if I wanted to throw away something, if I said, look, yes, you're in a two-dimensional space, but I only have room for one dimension. I can't deal with a second dimension. What would you do? Well, you would say, well, this dimension is clearly more important in terms of representing the data. So what do I mean by that? Take this axis here that you see and project all the data onto the axis. How do you project? Take a dot product. That's what we did when we did the basis transformation earlier on. Well, then you've got most of the discriminability of the data. You've lost a little discriminability in this dimension. But think about the alternative. What if I project it onto this axis? Well, then all the data would get slammed into this tiny little region. And so the eigenvector associated with the largest eigenvalues are the axes in the new basis that preserve as much data as possible with respect to the original dimensional space. There it is. That's dimensionality reduction. We are going to reduce dimensionality onto a new orthonormal basis, and the axes we are going to choose are going to be the maximal eigenvalue eigenvectors. Now, how many? Well, from 2, there's only one place to go down to 1. But if we start in a 100-dimensional space or a 1,000-dimensional space, how far do you want to go? Well, we're going to talk about that when we start applying these to images. But here is the core of PCA. Zero mean your data, compute the covariance matrix, compute a bunch of eigenvectors, and then project Decide what you want your dimensionality to be. 3, great. Take the top 3 eigenvalue eigenvectors, project the data onto those by just taking an inner product onto all of them. After all, it is an orthonormal basis. And you will have reduced dimensionality from wherever you started down to 3, down to 2, while preserving as much of the structure as possible. Okay, so these are really nice examples, but we should see what this looks like with images. And before we do that, we're going to get stuck a little bit. We're going to run into some computational difficulty. So we're going to resolve that, and then I'm going to show you an application of PCA to things like face recognition.